Hey, what's up? So I've had this relatively dumb research idea, and people have been asking me for more coding videos and so on. So I thought, why not do a video where I take a research idea and implement it from scratch, just to show how one would go, or how I would go about implementing something like this. Now, this was simply meant as sort of a demonstration, but then at the end it actually worked. And so yeah, that was unexpected, and my initial reaction was just to be like, oh crap, just hold everything, stop video making, you develop the idea, write a paper about it, okay? And I was about doing that when I realized that I'm always the one complaining that research is not transparent enough and people aren't open enough and so on. So I sort of thought I might do a different thing right here, in that I will actually share the process of this non-finished research project. So currently I am in the middle of this. I have no idea whether it's going to work out or not, and that's it. And I think we can do open source software development, completely in the open, whereas with research we're all like super scared that people are going to scoop us, and people will just keep their work hidden until they're done, and then boom, they put it on archive and all. I want to go to a world where we collaborate much more in research, and it's much more like open source software development. So here's my here's my process of implementing this idea, and it's fairly long, so if you just want to get to the results, you can just skip at the end. I'll put timestamps in, and there's this new YouTube chapter video, so that'll be very helpful, I guess. Yeah, and with that being said, I hope you enjoy this. Let me know what you think of videos like this, and I'll see you next time. Hey, what's going on? Today we're going to take a research idea and implement it as fast as we can. So this is not really to show you the best research idea, because it's not, and it's probably been done before, so I have no high hopes here. But this is just to show that if you had like some research idea and you've actually done the literature research and figured no one has done that yet, which I haven't, because probably someone has done that, how you could take this and like get started up initially pretty quickly. And this is just the process that I would go through, and I'm going to go through with you today, and we're going to try to get this up and running as quickly as possible. So I had this idea that looking at SimClear v2, there's a lot of things to be done still in the space of, let's say, self-teaching, self-distillation, and so on. There's mean teacher, and then there's whatnot. And this is all usually done in the semi-supervised, very few label regime, and so on. But we know that these self-supervised techniques can help you in supervised learning. And then in SimClear v2, you do semi-supervised, in that you do self-supervised, and then fully supervised, and then distillation, like self-distillation. There's all this kinds of interleaving stuff, and I thought, okay, what if I just take a pre-trained network that performs really well on something, and I self-distill it into a bunch of student models, like a number like 10 or so, and then that's my ensemble model. Will that perform better than the original model? Like, this is a terrible idea. It's probably not going to work. Like, there's 99% chance it's not going to work. But let's try to test this today. So I got my drink, I got my carbs since it's weekend, and we're going to give this a shot. All right, so first thing, we need some sort of base to go from. In research, it's good to build your own stuff, but a lot of the times, if you want to be as fast as possible, you want to go as quickly as you can. So here, I found this repo, thankfully with an MIT license. So shout out to Huiven Fun, I guess. For putting up a repo, training these CFAR10 models, or training these PyTorch vision models on CFAR10. CFAR10 is a small enough data set so that we can kind of work with it, and these models are already pre-trained. So I've cloned this repo, and we're going to adjust that. So there is first of all, there is a download, as you can see here, which in this repo it says it downloads these. I've not done this before. I have no clue how this is going to work out. In this download script here, downloads the weights from Box, and I hope you can see this. And then I guess you can load the pre-trained weights with pre-trained equals true, and yeah, we'll get into all that later. So the first thing we got to do is get this to run, let's say. So let's look at this downloads thing first. So the download thing is going to have a URL. It's going to use requests to get that URL and then save this into this state_dicts thing. Now, what I usually want to do is I want my folder of code to only have code and not to be intermixed with data and code, because this is the thing that I'm going to ship around to various servers and so on. So I'd rather have the code in one folder and then the data in like a central folder. So I'm not really fine with this sort of downloading this right here into the folder that we have. So what I'm going to do is I'm going to change that such that it downloads it into a central folder. So first, we already have OS. So what we're going to do is we're going to get some like data path going, which is going to be our home folder, OS path, and I guess I already have a CFAR10 folder right here, so we'll use this. And then, so path.join, we'll join that, and that's going to download. It's not really data, is it? It's more like models. Okay, let's do this. Cool. So data path is the models that is going to download. All right. And then it unzips the file again. So here it unzips the file to the current working directory. I don't want this, so I'm going to change that again to the models path. All right. Nope. Directory to path to zip file, directory to extract to. I think we're fine right now. So this download script is going to download the path, all the weights there. Now, I want this to happen sort of automatically while this is in a server, or while this is on a server. So what I'm going to do is probably just to, so if this script runs, you can see it runs the main, but in the other script, I might just want to do this automatically. So let's go to the test script right here, or let's say we go to the train script. This is probably the main script right here, the train script. So we have to somehow call this other script here, probably in the main function. All right, so let's import this other. So import CFAR10, what was it called? CFAR10 download. Okay, and here we're going to call that. And does this not download it if it already exists? We have to check that. So a lot of this is just going to be, beating stuff into existence. So if this zip file already exists, we're not going to do anything, right? Which leaves us open if the unzipping fails, then we're going to be in a kind of dumb path, but we'll risk it. Zip path would be that. So let's, if OS path exists, zip path, then return. Okay, so we're good in the download script. What else do we need? The dataset. I probably already have the dataset from Torch Vision, so that's not going to be an issue. Okay, so here we're going to call CFAR10 download.main. All right, and that should do. We can't really call that yet. Let's actually just run this download script. No such file or directory. Probably need to make that directory, right? Okay, if os make there's models path exist, okay, true, yeah, that should be something. All right, and we're downloading. So this is 2.4 gigabytes, which can, be put by itself. Let's put that over there. And while that's downloading, let's check out the test script, actually. Let's check out the test script. So this simply takes in this CFAR10 module and instantiates a trainer. And as you can see, it calls test on it. So this should not be too hard. I'm going to guess this CFAR10 module is a Lightning module. As you can see right here, it is. We know how PyTorch Lightning works. If you don't know how PyTorch Lightning works, pretty easy. You configure this module right here. You configure a bunch of stuff like the data sets, the training step, and so on, and you're good to go. So I guess what we're going to do is we're going to change this train script and change it to our needs. Okay, so let's copy that. Let's go with train ensemble. Bang. So this is what we're going to change. All right, so first, if the GPUs is a string, then yada, yada, yada. If it's 2, then, wow, that's that's kind of a weird engineering quirk right here. Okay, what I want to do is make the GPU use transparent. So we'll only ever use one GPU. So let's call that CUDA and put that to true. And then we'll say oh, come on. There's like a lot of stuff going on here. And then torch is called torch. I'd hate that. Can I do this? Can I import it like twice with different names? Probably. It's probably not very good, but I'll do it. Okay, so if CUDA is not available, we'll just set the CUDA to false. If th.cuda is available, okay, not if it's not available, then hparams.cuda equals false. And then we'll set the GPUs to 0, comma, I guess that's what it expects, if else none. And that should do it for the GPUs. Okay, so second thing that we need, we're going fit here, and there is this logs directory where the checkpoints are going to be saved. I'm fine with that. I just want to kind of remove the logs directory at the beginning. So I'll do that. And whenever we start this, I'm going to remove the logs directory. This is a controversial move, but on remove tree, recursively delete the directory tree. Yes, logs. Good. Okay, our download is done. So what do we do next? We might want to do just try to test something. And here in the test thing, we might want to set the GPUs. I don't have a GPU right here, so none. And the data directory is going to be, yeah, I'll put it. So nope. okay, it doesn't find the state dicts and so on. Now we're going to have to fix this. We're going to have to fix the fact that it doesn't load. Okay. Okay. And that's probably going to be here in these models. So if I look in the dense net, for example, which we can learn, and there's this pre-trained argument, and what's that going to be? It's, oh, that's bad. Okay, it like has hard-coded the fact, that there is this state dicts directory. Okay. Yeah, that's terrible. Terrible. So I guess this is going to be in every single one of these models, and that's not good. So what we're going to do is probably always load it without the pre-trained, and then kind of load it ourselves from the correct directory. So what's the correct directory? Again, we're going to set the model dir. We probably can just take that from the download script. Like that. State dicts. Okay. And then we want the architecture. I guess that's a thing we can actually put the classifier here, right here. That's something we can. So it's going to be the classifier. If you look in the state dicts directory, I'm going to guess you can models cfar10 state dicts. We haven't unpacked it. Where have we unpacked it to? Help. Oh no. Have we unpacked it to here? We have not. So what is in here? It's a cfar10 models something and then state dicts. Okay, so it's always going to be the architecture plus pt. So we can, we can deal with that. So it's going to be cfar10 models, state dicts. That's fine. And then it's always going to be the architecture plus a pt. So let's look at one of these models to see how this is loaded. We've seen this here. So we simply want to load this state dict in. And here it constructs the thing. Let's do proper string interpolation, shall we? Oh, device. Where does device come from? We should check that out. Device is given. Device, CPU. Where is device given? Okay, densenet, device, CPU. Oh, I guess device is always CPU, and then we map it to wherever. I'm not entirely sure. So here we say set device. I guess we can just get the device from somewhere. Let's try it out. Okay, so we're going to need this right here. So we're going to OS path join models path and something that's .pt. So, and here we're going to get the architecture, which is the classifier. Cool. So that's how we load something, and then the device, maybe we can just go torch cuda.get device. Is that possible? Let's try. Nope. Okay. Nope, no get device. Device, maybe? Nope. Map location was given. Okay. So we have to figure out where this device comes from, honestly. Here, no module. There's this get classifier right here, but that just says pre-trained. Is device always CPU? I just can't believe that. I guess I'll believe it. We'll always load to the CPU. Okay. Cool. We can do that. I guess PyTorch Lightning will then put it on the GPU for us. Cool. So this is about how far I got when I tried to do this by myself. And now the problems start. So, missing keys in state dict. A lot of missing stuff. We can't possibly load. That, yeah. No, not going to. So we can't load stuff. What does it do? Load file name equals, and then let's paste this. And let's put some kind of breakpoint here so we can check it out. Okay, that exists, no? It feels like that should exist. Yeah, that exists. What's the deal? What's the matter here? So we got model, which is, I guess, a ResNet 18. And we got this thing that we might want to load. So why doesn't it work? Torch load file name. See, that works. So that's the state dict. Is that. Let's look at its keys. We got a bunch of stuff. Okay. So why can't we load that? Model load state dict. State dict. And now unexpected keys in state dict. Missing keys. So this is always prepended with model dot, and here it's not. Okay. What do we do about that? I guess this is because we loaded ourselves. Okay. Cool. So our model is not. Yes. So our model has the subpath model. So we need model.model.load state dict. Right. Look at us. We made it. So this is testing. I guess this is this ResNet 18 or whatnot. So we can leave that to run for itself. So we figured out how to load this stuff. Took us a while. Now, let's go ahead and we know how to load the models. We know how to load the weights. So this is our teacher model, right? Our teacher model is supposed to load up the weights and then teach the student models. So here, what does this training thing do? We download the thing. We make our GPUs to be really good. Okay, and then we instantiate this module right here, as you can see. So now we're going to check out this module. By the way, the testing is done, and as you can see, there's an accuracy of 93.33, which I'm pretty happy with. This is congruent with what we saw right here, the ResNet 18 do. Okay, and I guess we can take a ResNet 18 or a ResNet 50. They're both fairly small right here, so a lot of them are going to fit on our GPUs once we use the GPUs. So let's change this module around right here to actually do the let's say the proper thing that we want it to do. So here we have self.model, as you can see, and it's get classifier, and the question is, does it load it pre-trained? So what we want to do is, this is going to be our teacher model. And in this get classifier, we want pre-trained to be false always right here. We don't want any sort of, we don't want to load the pre-trained. Instead, what we want to do is we actually want to have we want to load it ourselves, right? So here pre-trained false, and now we're going from our test script, we're going to take over the path, the code that we used to load this. Okay. All right. So bada bim, bada boom. OS, we don't have OS. That coming along just fine. Yep. So now here we're going to have our self-teacher model to load that state dict. All right, so this is it for initialization. Now we also need our student models, of course. So our student models are going to be a bunch of models. Models are going to be a bunch of models where, what do we say? So this is going to be a torch or a module list. There's this module list. Torch.nn.module list. Right? So I initialize that with a list. And the list is going to be get me the classifier. And we're just going to go for the same kind of classifiers right now to really boil it down, to have the same architecture for the student and for the teachers. For bar in range, and here we probably need a flag. So hparams.num students. Okay. So these are going to be our student models. So let's quickly create this num students thing right here. I'll probably have to have an integer. And we'll go with 5 students for now. Okay, so we're creating 5 students. All of them are not pre-trained. So are we going to train them from scratch, or do we want actually to take over the weights? We probably don't want to take over the weights. Let's just train them from scratch in a distillation mode. I have no clue about this stuff, by the way. Okay, I guess this already concludes what we wanted to do. So I guess this module list, what can we do with it? Does anyone know? I don't know. By the way, I'm sorry for the switching between the dark and the bright background. I don't know how to fix that. So PyTorch NN module list. It would be nice if we could give them some names, right? So I guess that's just an iterable right here. So probably there's nothing that we can do to give them proper names, or we'd have to hack around. And I don't want to do that. So I guess we can just check if that actually computes until here. So let's check it out. Let's try the ensemble. It doesn't. Dataset not found or corrupted. Okay, so what we'll have to do is we'll have to change this data directory right here. So the data dir is going to be OS this, whatever my C410 directory is. No such file or directory. Logs. Okay, so logs doesn't exist, so let's actually make it. Still no such file or directory. Logs. Why? Why doesn't it make it? No such file or directory. Logs. Ah, okay. We need to ignore errors here. And we're good. Okay, so it computes until the point. You probably can't see that, right? I guess now you can see it. Let's check. Yeah, now you can see it. All right, so where are we? We are at the point right here in our module after we've created the teacher and the students. So if we look at self, technically, we should be able to see right here a whole bunch of ResNet 18s. Whole bunch. So here you can see the teacher model, right? And I'm going to guess you can see layer 4, and here you can see the student models. So the student models are going to be in a whole list of models. And now we're going to train them. So since they're initialized differently, our hope is going to be that they're sort of going to end up at different places. We're going to train them with the same, like we're going to be really, really stupid about this. Okay. All right. So let's be really stupid about it. So what are we going to have to change? Here is our training step, and our training step is actually fine. We'll simply forward, we'll get a loss from that, and then we are going to return that, and that's going to be backpropped. So in our optimizer, wherever we initialize our optimizer, we should probably give it the parameters that are not only the student model parameters, right? Not the teacher model parameters. So it should only train the student models, okay? And even like that, we should probably always set the teacher model in eval mode. But we'll do that in the forward step right here. So in the forward step, we get images and labels. And here it runs it just forward through the model. We want to change that. We actually want to have teacher predictions, which we're going to have the teacher model. We're going to forward this through the teacher models. Now the criterion, I'm going to guess, is a cross entropy. So the predictions here are actually going to be logits, right? And this is good, except that what we want to do is have a distribution of over labels. So after the teacher here runs through, and let's put a breakpoint right here and actually look at it. I find it's always easy if you go and just run until the point where you are at the code, and then you can just look at stuff. So here there's a validation sanity check. Okay, probably don't want that. And now we have the break right here. And now we can look at teacher predictions dot shape. So that's a batch size times 10. And if we look at it, I'm going to guess there's some negative numbers in there. So that's not going to be that. Those are going to be logits. Now we want that to be a soft max over the last dimension, and that's going to be of the same shape. But of course, now we're going to have a proper distribution. So if we sum over the last dimension, you should see a bunch of ones. All right, so the teacher predictions are going to be softmax over the last dimension. And since we don't want to backprop through the teacher, we can do this in an environment of no grad right here. So we have that with not being stupid. And we also set the teacher model into eval mode. So I guess that does it. Set train? No. That should do it. I have no idea. Yeah. Let's run it again. We could have done that there. Okay. So far so good. So we have the teacher predictions. Now what we need to do is run them through the student and use them as labels. So we'll go for student in student models. We'll go student forward, or we simply run the images through that. And that gives us the logits. And then we use our loss function on the logits. And not the labels, but the teacher predictions, right? So we never actually use the labels here, as you can see. And that's going to be the student loss. And now we have a bunch of losses. And we're going to append that. Nope. Dot. Like this. And our loss is simply going to be the sum of all the student losses. Not even the average. I guess we could. Losses. I guess we could make it the average. Just so if we change the number of students, we'll get some sort of a better sense of the actual numbers. What? Okay, I think over here we're good. Yeah, so our teacher model is not in training mode, but our student models, hopefully, are in training mode. No? Is this the eval pass? I guess this is the eval pass. This is the validation sanity check pass. Okay, so this is going to be our loss and our accuracy. Now, right, so okay. What's going to be our accuracy? Our accuracy is going to be, we have these student losses, all of them, and what we are going to do is we're simply going to take the maximum prediction across the students. Right? Pretty easy. But we need to collect the logits. So come on. So we'll also have the logits, append the student logits. Okay, so we have a whole bunch of logits right here, and we'll get some predictions out of that. Now, the question is, do we want to simply take the mode, or do we actually want to run a softmax over each and then take the average prediction? I'm not super sure, but we can try to do it in different ways. So right now, we might just want to take maybe the average logit and then run a softmax on top of that, because I'm going to guess the logits are outputs of a linear layer. So they might behave more in a linear fashion than if we were to average the actual probabilities that come out. Right? Maybe. Let's do this. Okay. So we'll take these logits. They're all, and we need to somehow concatenate those or stack them. So how are we going to stack them? So they're 256, they're batch size by number of classes. So we'll just stack them at dimension 0. I guess that's fine. And then we are going to mean also across dimension 0. So those are going to be our logits, our final logits, and then our predictions are going to be the argmax of the logits in the last dimension. Yep, that should be pretty straightforward. I guess that's it. Easy as that. Yes, the rest here should just do by itself. And I'm going to go ahead and give this another run and see where we run into problems. Can't really see how this could ever go wrong. We'll just take everything over. Okay, we actually got a problem. 1D target tensor expected, multi-target not supported. So the cross entropy loss in PyTorch does not support that. Let's give it a shot. I'll make this a little bigger for you. And let's go for the cross P loss. I can't type today. So here we have the cross entropy loss. And the cross entropy loss is useful when training a classification problem with D classes, yada, yada, yada. Weight should be 1, yada, yada, yada. Okay. Criterion expects a class index as the target. Okay. So what we need is like a soft loss, right? We don't need this cross entropy loss. We actually want to have soft targets. So what do? We want to do, I think the cross entropy loss is a combination of the log softmax and the NLL loss. Can we take the NLL loss maybe? So the NLL loss right here is going to be the target that this loss expects should be a class index. No. Okay, that's not good. So next, let's go. Do we have... We somehow need a soft cross entropy loss. Let's search for that. PyTorch soft cross entropy. Soft classes. I guess people do that kind of stuff. So the problem with these kind of losses is that what you have to do is kind of protect yourself against numerical instabilities, right? So what we want to do is find a function that does this for us. I guess if we do the log softmax, that should take care of it for us. Okay, this is TensorFlow. Okay. Following thread, cross entropy loss. I guess people just do really the log softmax and then do that. And we should be fine with this. Okay. Thanks, K. Frank. Yeah, maybe this has advanced since then. So we can give like a last look at this, and this is a bit too big. I'm sorry. Your eyes are going to have to suffer. And we're going to look at loss functions, and we're going to just look through them. Multi-label soft margin loss. Multi-label. We don't really want multi-label, right? We want this, but not with the targets. Okay, I guess we're just going to have to write this ourselves. So ultimately, what is the cross entropy? The cross entropy is simply the probability of the true label times the log probability of the wrong or of the predicted label, as you see right here. So we are going to simply multiply target times the log probability of the predicted label, and then take that mean across the batch, I guess. Yeah, that should do. We can implement this. Let's do it. So this criterion right here is going to be our loss function, and that's only used once. So what we can do is going to be a function so we're going to take student logits, and we're going to take teacher probabilities. Okay. So how's that going to work out? We're going to do the log softmax from the student logits. So nn dot, does that exist? Log softmax functional. Okay, we need functional. And student logits of that dimension. So now we have properly normalized student logit. So that's going to be student log probs. And then what we want to do is simply multiply the teacher probs times the student log probs. And the negative of that is going to be our loss. The question is, do we want to sum that, I guess, across this dimension, or mean it? I guess the sum should do. All right, this is it. Easy as that. Why have we searched for so long? So the criterion, we can simply replace that now by our loss function. Cool. So let's run it again. Yada, yada, yada. Okay, sanity check. Maybe we should have taken like a smaller model. It sometimes pays off to, you know, start with a really small model, just so you can do these kind of things fast. So here we have dimension out of range. Okay, which is, where is that? In forward, in line 78. Let's go there. Line 78. Okay, here the max is not going to be as much fun. Let's go there. I think this is, some of these things change over time in PyTorch, so this code might be written when, you know. So what we have is, we have a max over the predictions, and the predictions, oh, it's already an argmax. So I guess we can remove this all. Whether or not that agrees with labels.data, we don't need any of that. .float, and we also don't need that. So the accuracy is simply going to be the mean of this. No? I guess. So we're here. Can't we just do predictions equals labels? Yes. And we want the sum of that. Actually, we want the float first, and then we want the mean. Yeah, that seems reasonable. So let's do it like this. Float mean. Perfect. How could this be any more easy? Well, this right here is all a bit. So validation step, accuracy corrects. We'll just look at it once we've done it. And what I do is usually just run it until it doesn't give me any mistakes anymore. And then I know I sort of have succeeded. Okay, we're pretty close, I feel. So it says grad can implicitly create it only for scalar outputs, which probably means our loss function is not a scalar. So when we return the loss right here, here we have the sum of the losses divided by the length of the losses. Let's go here and check out what's up with that. So what we'll do, I see, this loss function here will output basically one loss for each data point. So what we need to do, I guess, is call mean on this, or sum. When they created the criterion in the original one, now we've thrown it away. Look at the git diff right here. So I guess this reduces, how does this reduce the cross entropy loss when we don't do anything? The cross entropy loss reduces reduction mean. Okay, so let's reduce with the mean. So if we call loss, then after that we should call mean. And then here, I'm not so sure anymore we should divide here because the learning rate is kind of tuned to the original loss size. So I guess we'll be content for now with summing up these things. And over here, I guess we've solved that, right? No losses. Yeah, see, our losses is going to be an entire tensor. And now we just fixed that right now. Okay, so let's try it again. In the meantime, what can we do? We can, so we already take care of our GPU, we take care of the logs. One thing to do with respect to this download stuff right here is, you know, if you have a server or something and you let a lot of things run in parallel, what you want to do is make sure they don't all download the same stuff at the same time. That's pretty bad. So what you want to do is ideally have some sort of lock such that they coordinate. And I usually use a file lock for this. So I'm going to create that right here from import the file lock, and then I simply create the lock. Let's go file lock, and here you have to input a file. So sometimes like, yeah, data lock, I don't know, you just pick some file, and that's the file that these processes are going to sync on. And then once you do this, you simply wrap all of it in a with lock. So only one at a time can go in this function. All right, so that's that. That should make us safe. And right here, we're now training. This is excellent. We are training the students. Now we need to do that on an actual GPU. So I have multiple tools to ship this to a GPU. So first of all, I can try to ship this to a, let's say, to one GPU. So the way you do that is, first of all, I want some sort of unbuffered version of Python. And then I have this, do I even have this tool? I do have the tool. Okay. So I'm going to call one of our servers. And we don't know what's going on. Okay, so cannot import name seed everything from PyTorch Lightning. Seed everything. Is that some kind of new thing in PyTorch Lightning? I guess I have it, apparently. So here, seed everything with 0. Why? I don't need that. We are running without any seed here. We are being really cool. Okay, next mistake. Cannot, okay, still same mistake, of course, since we don't. Yep. Next mistake. We'll just go through the mistake. Learning rate loggers. So I guess we need to update PyTorch Lightning on the servers, and I'll do that quickly. Okay, I've updated PyTorch Lightning. Let's check out whether or not we can actually run something. Yeah, we can run something. So this again is now downloading this on the server. While this is happening, there's another thing we can do. Namely, I have sort of made a system to run stuff on servers, which I like a lot, honestly. So I guess we can try this out. How do I hidden? Oh, with I. Okay. So I want to first of all delete this. Delete this. Yes. Yes, delete this. Cool. And this Git folder is a bit annoying. Let's restructure, because otherwise it'll always ship the Git folder with everything up here. Does it do that? Yeah, I don't like to have the code in a top level. So quickly make a sources directory, move everything in there. So move the C410 models into the source directory, move all the Python files into the source directory. Nope. Clear the logs, and we're much better, much better. Okay, much better. So what we will do is, my system requires like a file, and I'm just gonna copy one from another project quickly. Okay, so we're back, and I copied that over. As you can see, you basically give hyperparameters and it blasts the hyperparameters through in a kind of a random search fashion. It's not too sophisticated, but we can work with it. So 10, that's the file, right? For 10 train ensemble. Yes, that's the file. Cool. And here we're just going to put all of our hyperparameters. And that will remove the logs file. I'm okay with that, but I want this. Bang. Cool. So what do we want? We want, basically, we just want to try it like a bunch of times and then see like average across it, right? That's all. Maybe we want the architecture to change. So let's say the classifier is a ResNet 18 or a ResNet 34 or a ResNet 50, just so we have a bunch of stuff to do. Okay, and this downloaded and is training on GPU, hopefully. If this works, then we can ship this off. And we'll make this other hyperparameter that I like to use called rep, which is just basically a dummy parameter. And so I can just repeat the experiment a bunch of times. And let's put that in here. So this is really, this has no effect, except for randomizing it a bit. I guess we can try to seed stuff. So whenever it says seed everything, we'll just seed it with this. We'll call it seed. No. Is it here? This seed everything? Yeah, so hparams.rep. Seed. Cool. With this is doing something. Nice. You can see, so this is unbuffered Python output. Thanks. Yeah, so what other classifiers do we have? We can try a bunch of them. We can try all of them. Why don't we try all of them? Like this, then let's go into this rat file. I don't know why I called it rat. I just wanted like some 3-letter thing. So, yep, like this. And then we can just take all of that crap and delete it and delete this. And those are going to be all our models. So our classifier is going to consist of all of this stuff. Let's... I know. I suck at Vim. Don't tell me. Actually, tell me. I want Vim tips. Trying to learn something new like each week in Vim, but it is hard. And tend to make myself actually do it. So let's go with just one repetition so far. If we are not sure, we can still up the number of repetitions. Oh, we don't even have the rep right now. This is called seed. All right, so we have different classifiers. And what we're going to need, we also have this num students, right? Let's go with 1, with 5, and with 20. So here we got one epoch done. And did we get a validation loss? Did we get a validation accuracy? Validating. I have no idea. We'll cancel this right now. And we'll go ahead and just blast this onto our servers. And hopefully that's going to work. I have no idea. Is everything fine? Everything's fine. Go. No. What? Cool. And let me get back to you once this is finished. All right, we're back. So I've just written some code here to extract the results of that run. And something, it's pretty interesting what came out. So in these plots, you'll see on the x-axis, you have the number of students in the ensemble. Remember, these students are all trained from the same teacher. The teacher you can see in orange, that's just a single teacher for reference. You can see that if you have one student model, it sometimes underperforms or sometimes outperforms the single teacher model. But then if you have more student models, you can see that there is a pretty monotonic relationship. So here it's the reason this doesn't finish here is because there's not enough space on the GPU for that many student models. But you can see that the relationship here is fairly monotonic. Here it's a bit of a kink. So the first idea, like this is really astounding because these students have all been trained from that single teacher, and they have been trained for as long as the teacher has been trained. So they don't have more compute than the teacher. They've been trained from scratch, not from some checkpoint or from the teacher weights. It's simple distillation from the teacher, no labels. And the students are all in parallel as well. So they don't see different data or even different data augmentations. It's the exact same order of the exact same data points going through all of the students, the exact same learning rate schedule. There's no noise and so on.
So the first thought that came to my mind, like something fishy is going on here, right? Like this seems like too, like, come on, there's no new information here. So I thought, hey, the teacher model, I've just grabbed them from this repo, from this pre-trained checkpoints. And these pre-trained checkpoints, they are, the checkpoints that have performed best on the validation set. So this is sort of a sneaky way of how we could train on the validation set, right? Because we annotate each data point in the training data set with this checkpoint. And the checkpoint has been selected for performing especially well on the validation data set. It could explain why we get a gain on the validation data set. So what I did is I retrained all of the teacher models such that I just retrained them for these 100 epochs, and I just took the last checkpoint. Everything's the same. The hyperparameters, learning rate, schedule, and so on. This is not tuned for any particular model, and it's pretty standard. It's not like 0.12589, it's like 0.01 and 100 epochs or so. Fairly standard parameters, and I just took the last checkpoint to make it, didn't even look at its performance, to make sure that I didn't select something that was especially good on the validation data set. And the results here you'll see are actually already the results of that run, which the previous run, it was almost the same. Like, I was astounded at how well it works, and then I thought, hey, maybe I'm kind of cheating here. So I redid it with the teachers that are not specifically selected, and this is already the results. So that's pretty cool, right? So then I wondered, what happens if I increase my training amount? So I just let this run for more. Like, what if I let the students run for more than the teacher has run? Again, there's no new information here. So you can see that the green is now the teacher, the blue is 100 epochs, and the orange is 250 epochs. And you can see with that, even one student will outperform the teacher, but many students will outperform even more. So if you give more compute, there's lots of headroom here to improve. You'll see this here. I think this last one with the blue line is just a bit of a weird configuration. I guess if you were to rerun that would fall in line. So this is pretty weird, right? So I have a bunch of questions. So first of all, I've searched the literature a bit more, and I came up with a number of papers that do things like this. Now, usually when you do distillation, people stress the importance of like how to introduce noise, like in the noisy student paper, or that you really need these data augmentations, or SimClear v2 uses the self-distillation in order to do in order to label more data. So they say it's important that we bring more unlabeled data into the process, and so on. So all of this, it really doesn't match right here, and especially this focus on we need noise during the distillation process to build these ensembles. This is also, if mean teacher, things like this. I also found a paper called Born Again Neural Networks that does something quite similar, but not like the same, where they distill a teacher to the student with the same architecture, and then they distill the student again into another student, and then that into another student, and so on. And then at the end they say, oh, we can also build an ensemble. But sometimes their ensembles outperform their chain of distillation. Sometimes they don't really focus on that part a lot, and it's way more complicated. Like, you distill one student after another, and I also think they have some introduction of variability in the students, like noise or different augmentations and so on. So this here seems really simple. Now I want to know this ensemble effect. It seems pretty weird, right? So what gives? So the first thing we could do is we could say, how does this compare to an ensemble of teacher models? Like, if we actually were to build an ensemble, like train 5 teacher models on, five different teacher models, it's still the same data, but reasonably they might be able to learn something more from the data. If we have 5 teacher models, they might learn different things from the data, and therefore if we combine them, they might kind of overlap their knowledge and sort of catch where if one doesn't generalize in one data point, the other 4 can overrule it. Whereas with these self-ensembles, there's not really a way where we can learn more from data, because we can only learn from the teacher, and the teacher is fixed and has seen that much data, right? So how does this compare? So I rewrote some code. It's just plumbing, and I released the code. It's linked, but it's just plumbing. Don't worry, don't worry. There is no great thoughts in there. It's just plumbing, such that my students are not all in parallel. So the ensembles are not trained in parallel anymore. I train each model individually, which means that at maximum I have to have 2 models on the same GPU, 1 teacher and 1 student. So I make sure that the teachers, they are trained from scratch, and the students, they're always trained from the same teacher, right? So the student ensembles will be exactly the same as we have them here. That means 1 teacher is responsible for all the students, but yeah. So, okay, I'll just show you the results right here. So if we look at those results, you can see that, and I've done it for a bunch of models right here. The blue line is the ensemble of teachers, and here on the x-axis you see the number of models. And now, since I'm not training everything on the same GPU, but I recombine later, that basically means that I have the ability to train up to 10 models, or actually however many I want. And the only real trick in the code is that when I evaluate one of these ensembles, what I do is I load a mini batch, and then I basically load the first checkpoint, run a forward pass, load the second checkpoint, run a forward pass, load the third checkpoint, run a forward pass. I do this for all the checkpoints until I go to the next mini batch. But that's just for evaluating, right? It just seemed easiest with the code that I had. So you can see right here that there is a significant, like this is almost overlapping right here. For most models, sometimes the student wins, sometimes the teacher wins. So the teacher ensemble wins. Now, remember, the teachers are trained on 10 times as much data right here. But it's always the same data, but still they have the opportunity to learn 10 times as much information from the data. Whereas the students, they're all distilled from that same teacher without any noise, any augmentations, except for the augmentations that you use during training anyway. And I've done this for 100 epochs, and I've done this for 250. Is this already 250? No, I think that was 100. I just put that there. Nope. Okay. Yeah, that was 100 epochs. But you'll see the 250 epoch plots, they look very much the same. Okay, they're just a bit better if you train for 250 epochs. Now, interestingly, okay, here's the interesting part about the 250 epochs. The student is still distilled from a teacher model that has been trained for 100 epochs. So, I mean, all of this makes no sense to me, right? The student is still distilled from the 100 epoch teacher model, yet if you train the student for 250 epochs in self-distillation and then build an ensemble of these students from that same teacher model, and you compare that to an ensemble of teachers that have all been trained for longer, for 250 epochs, which, the 250 epochs generally outperforms the 100 epochs models. Still, they are the same. This is pretty crazy results, I think. And sort of my conclusion from this is that the ensemble effect right here is not a function of learning, of extracting more information from the data. The ensemble effect might actually have something to do with the function landscape itself and kind of exploring different minima of the same function, not of the same function, but exploring different functions to describe the same phenomena. And I've also found a paper that explains the loss landscape of deep ensembles, and I will make a video on that. Maybe it's out already, maybe it will be out after you see this one. I haven't decided yet which order I'm going to release things. But this here, it's pretty interesting, and we need like a name. So self-ensembles are already a thing, but they are always with noise and stuff like this. So let's call them something like plain self-ensembles. Like that sounds like a good name. Plain self-ensembles, the act of self-distillation, a single model into multiple models without any noise, any augmentations, anything. Just you run as if you were to train the model itself. And then you build an ensemble of these models by simply averaging the logits. Plain self-ensembles. All right, so the plan from here is to check on like at least one other data set. You know, these models, I appreciate that I could get them pre-trained, but they're just the ImageNet models and then kind of let run on CFAR10. So there's no kind of guarantee that these have been, you know, tuned or anything, that the learning rates or whatnot. So I want to take like an ImageNet model, still make sure that I don't use any like hidden information where I could cheat on the validation set, but try this on at least one thing and see if that works as well, if we can sort of push ImageNet performance simply by doing this trick. So that's the plan for now, and I have some other ideas, but I just wanted to let you know. And this is sort of how research works, I guess. You have a dumb idea and it turns out to work. And then you go on, and still probably there's not maybe too much interesting things here. Maybe it doesn't work on ImageNet because these models are just undertrained and this somehow made them better somehow or regularized them somehow. That usually doesn't work. There's so much that can go wrong still. So, but yeah, that was it. And I invite you to like check out other papers in this space if you want. It's a pretty interesting space. And with that, I don't have much more to say. Yeah, I hope you enjoyed this. Let me know what you think of like research implementation or research process videos like this. I'm not sure what people expect. Like I can't make this into a 5-minute video of like, woo, I discovered something, because then, you know, there's no clue of what's happening. But maybe like an hour or so is also too long. I'm not sure. Yeah, let me know what you think, and I'll see you next time. Bye.